Hello again, this is Professor Roman. Let us continue the lecture series on Transition to Advanced Mathematics. We are discussing binary relations in this chapter, but there are other types of relations besides binary relations. And I want to go over those with you briefly. We're not going to do a detailed study of those types of relations other than the binary relations, but at least you should see the terms so you'll be aware of them when you encounter them in your future studies. So let A be a non-empty set. A unary relation is just a subset of A, so it's a synonym for subset. One would normally refer to a subset simply as a subset, but if you're studying relations on sets, then you might use the term unary relation. Binary relation, we already know, is a subset of A squared, which is A cross A. A ternary relation on A is a subset of A cubed, so that's A cross A cross A. And in general, if n is bigger than or equal to 1, an n-ary relation on A is a subset of the Cartesian product A to the nth power. So that's the Cartesian product of A with itself n times. Some examples. You don't really need an example of a unary relation because it's just a subset, but it's here anyway. A is the set 1 through 5. Then this R is a subset of A, and therefore it's a unary relation on A. The in-between relation on, say, the real numbers is a ternary relation, and that's defined by saying that the ordered triple ABC is in the relation R if B lies in between A and C. So A less than or equal to B less than or equal to C. Some of the terminology changes a bit. You can't say that A is related to something here. If it was an ordered pair AB, you'd say A is related to B. But when you have an ordered triple, you just have to say the ordered triple is in the relation. In general, for any n bigger than or equal to 1, we have a diagonal relation, delta sub n, which is the set of ordered n-tuples whose components come from A, and every component is the same. So that's a generalization of the diagonal relation on A that we talked about earlier. But from now on, whenever I use the term relation without qualification, I'll mean a binary relation. There are several important properties that a binary relation can possess, and the most important of these are listed in the following definition. There are 6 of them. And so to help you remember these, notice that actually they're grouped into groups that would look something like this. Reflexive and irreflexive are similar in flavor. Symmetric, antisymmetric, and asymmetric are similar in flavor, and transitive. So let's go over these. Relation on a set A is reflexive if every element is related to itself. Equivalently, the graph of R must have a loop at every vertex. R is irreflexive if no element is related to itself. And so in terms of the graph, there are no loops. So you can see that these two properties are, of a similar flavor, but they are exact opposites. They're not negations of each other. To negate reflexivity, you only need to have one element, one vertex, one element that does not have a loop. that's not related to itself. So these are exact opposites. Every vertex has a loop. No vertices have loops. There are three properties that are symmetry-like, or anti-symmetry-like. So first is symmetric, and that is, by definition, A related to B implies B related to A. Equivalently, in terms of the graph, if there's an arc from A to B, there's also an arc in the opposite direction from B to A. Antisymmetry is this: A related to B and B related to A implies A equals B. So another way to say that is that between every pair of distinct vertices, there's at most one arc. If you have arcs going in both directions, the vertices have to be the same. And then the arcs become a loop. Okay? So there's at most one arc between every pair of distinct vertices. Asymmetry looks like this. A related to B implies B not related to A. In terms of the graph, this is equivalent to saying, again, that there's at most one arc between distinct vertices, but also there are no loops. And that's something you may need to think about a few minutes to convince yourself that that's what this means. The final property is transitivity. A related to B and B related to C implies A related to C. In terms of the graph, what this would look like is if you have A, B, C, and you have arcs going this way, so A is related to B and B is related to C, then this arc has to exist. It completes a triangle, but you have to be a little careful about that language, because you might think that to complete these two sides into a triangle, you'd go the other way. So you have to be a little careful about that. Okay. Just to illustrate with it an example, this is a binary relation on the set 1, 2, 3. It is reflexive because every element, every integer is related to itself, indicated by the loops. It's transitive, and for that you have to spend a little effort. It's not so easy to see transitivity either from the graph or otherwise. For example, there's an arc from 1 to 2 and from 2 to 3, and so there has to be an arc from 1 to 3, which there is. There's also an arc from 2 to 1, and then from 1 to 3, so there has to be an arc from 2 to 3, and there is. And then finally, there's an arc from 1 to 2 and an arc from 2 to 1, which means there has to be an arc from 1 to 1, and that's this loop. So that is how you would check transitivity from the graph. This relation is not symmetric, because to be symmetric, if there's an arc between from A to B, there has to be an arc from B to A. Well, there's an arc here from 1 to 3, but nothing from 3 to 1. So it's not symmetric. It's not anti-symmetric, because to be anti-symmetric, if there's an arc from A to B and one from B to A, then A and B have to be equal. But here you see an arc from 1 to 2, another arc from 2 to 1, but 1 and 2 are not the same. This also fails to be asymmetric. Asymmetric would mean that if A is related to B, then B is not related to A. But again, this situation between 1 and 2 shows that 1 is related to 2, but 2 is also related to 1. Don't be discouraged if you feel overwhelmed by all these 6 properties. It's just a matter of using them for a while, thinking about them, doing some exercises, and it will become easier. But ultimately, you do need to, and in fact, when I say ultimately, I mean soon, like right away, you need to commit these properties to memory. I know that's a bummer, but it has to be done. I guess the most trouble you'll have is remembering these 3, especially the difference between anti-symmetry and asymmetry. But we all have to do it. I had to do it too. Symmetry is actually a very nice property when it's available, when it exists. Because when a relation is symmetric, then A related to B implies B related to A, and so you can use a phrase such as A and B are related. And that's very convenient. Without symmetry, that would make no sense, because there's a definite direction to relationships, okay, indicated by the directed arcs. Okay. So that's a big help when you have symmetry, but we don't always have it. The properties that we've been discussing, the ones that are described in the previous definition, are not entirely independent. And here are some connections between those properties. So the following hold for a binary relation R on a set A. R is asymmetric if and only if it's irreflexive and antisymmetric. R is transitive and irreflexive implies R is asymmetric. R is symmetric and asymmetric. Symmetric and asymmetric if and only if R is the empty relation, which means it has no ordered pairs, so nothing is related to anything else. R is symmetric and antisymmetric if and only if R is a subset of the diagonal relation. You don't need to memorize all of this if you can follow the proof, which is quite short. In each case, it's simply a matter of applying the definition. So let's take a look at the proofs. And I'm going to use the tilde notation for the relation. For part 1, we can first assume that R is asymmetric, which means that A related to B implies B not related to A. Well, setting B equal to A tells us that A related to A implies A is not related to A, which of course is a contradiction. The only way out is that no element is related to itself, which is precisely the definition of irreflexivity. So asymmetry implies irreflexivity. Also, the definition of antisymmetry, which looks like this, A related to B and B related to A implies A equals B. This is the definition, but asymmetry, which we're assuming, implies that this antecedent is false. You can't have both of these. And when an antecedent is false, as you know, conditional statement is true. So asymmetry implies both irreflexivity and antisymmetry. For the converse, suppose that R is both irreflexive and antisymmetric. then we'd like to show it's asymmetric. We'd like to show that you cannot have both A related to B and B related to A. If you did, anti-symmetry would imply that A equals B, and therefore A is related to itself. But that violates irreflexivity. So one of these two must always fail. So R is asymmetric. For part 2, this is just a conditional. Transitive, irreflexive implies asymmetric. So we assume that R is both transitive and irreflexive. Again, if A is related to B and B is related to A, we're hoping for a contradiction. But transitivity implies then that A is related to A. So we're back in the same situation we were in the previous proof here. Violates irreflexivity. One of these must always fail, so R is asymmetric. For part 3, I'm going to leave it to you to ponder the fact that the empty relation is symmetric and asymmetric. That will follow directly from the definition. In the other direction, we assume that R is both symmetric and asymmetric. And if A is related to B, then symmetry implies that B is related to A, but that contradicts asymmetry. So no element can be related to any other element. A related to B can never happen because of this, which means nothing's related to anything, so we have the empty relation. And finally, for part 4, again, if R is a subset of a diagonal relation, then it's pretty easy to see that R will be symmetric and anti-symmetric, and I'll leave that for you. In the other direction, we can assume that R is symmetric and anti-symmetric. Well, the symmetry tells us that A related to B implies B related to A, and the anti-symmetry then tells us that A equals B. So in other words, A related to B implies A equals B. So the relation is a subset of equality. This only goes in one direction. So R is a subset of the diagonal relation. So there you have the proof. What I would suggest is that you should really try to do most of the time is write down the theorem and on a blank piece of paper and try to prove this yourself. It will test your facility with the definitions, especially the most confusing ones, I guess, which are symmetry, asymmetry, and anti-symmetry. If you can construct these proofs yourself without looking at the definitions, then you're in really good shape. And you don't have to memorize these, because if you are asked on an exam, is it true or false that, say, this holds, you can sort that out by applying the definitions. You can check it yourself rather than having to memorize. Let's look at a couple of examples. The equality relation, E, on a set A is reflexive, symmetric, and transitive. Certainly it's reflexive, since every element is equal to itself. And it's symmetric, since A equal to B implies B equals A. And it's transitive because A equals B and B equals C implies A equals C. Actually, equality is the smallest reflexive relation on a set A. in the sense that if R is any relation, reflexive relation on A, then E is contained in R. So for the specifics there, say R is reflexive, so that means ARA for all A in capital A in the underlying set. In ordered pair notation, it's a little easier to see what's going on here. The ordered pair A, B, and E implies the ordered pair A, B is in R. If A is equal to B, then A is related to B under R because of the reflexivity. That's the same as saying that E is a subset of R. So another example, inequality on the real numbers is reflexive, since A is less than or equal to itself for all real numbers A. It's anti-symmetric, since A less than or equal to B and B less than or equal to A implies A equals B, and it's transitive. A less than or equal to B and B less than or equal to C certainly implies that A is less than or equal to C. But on the other hand, strict inequality is irreflexive. No element is strictly less than itself. No real number is strictly less than itself. And it's neither symmetric nor anti-symmetric. But it is asymmetric and transitive, and I'm going to leave all that for you to check. It's really good practice. If you're going to become comfortable with these properties, these 6 properties, you really need to practice. Another example, we've already discussed congruence mod K, defined this way. And there are some other notations. Sometimes we can just write the 3 lines here with a subscript K. Congruence mod K is reflexive, symmetric, and transitive, just like equality. Reflexivity just means that A is congruent to A mod K. But I think actually it would be better if I should have probably left these for you to check, because it's, again, good practice. These are pretty simple. Transitivity is a little bit testy, so you're going to have to do a little bit of work to check transitivity. Finally, if sigma is an alphabet, the same length relation on the set of words is also reflexive, symmetric, and transitive. Shorter than is asymmetric and transitive. And I'll leave that for you to verify again. You might have noticed then that several of the examples were reflexive, symmetric, and transitive. Turns out that there are 2 combinations of these 6 properties that are particularly important. They stand out well beyond any other possible combinations. Reflexive, symmetric, and transitive is one of them. Any relation that has these 3 properties is referred to as an equivalence relation. Equivalence relations are immensely important. If you have a set of objects, mathematical objects, and you find yourself wishing that some of those objects could be treated as being essentially the same, then the way to do that is to define an equivalence relation on the set. And we'll go into that in detail in a later chapter. But for now, not to worry. The point I'm making here simply is the combination reflexive, symmetric, and transitive is a very important combination of properties. Reflexive, anti-symmetric, and transitive is another very important combination of properties. Any relation that has those 3 properties is referred to as a partial order. So there's a sense in which these 3 properties capture the essence of order, whereas the first 3 properties capture the essence of equality. So again, I'll make all that clear in due course, so not to worry about it now. I want to talk about something now that you might not actually encounter in other courses at this level that discuss binary relations, which they all should do, and that is the idea of closure. So we'll do this briefly. What do you do if you have a binary relation that you are studying or that you need for another purpose, and it fails to be reflexive or symmetric or transitive, properties that you may wish it had? Well, that can be fixed. If a relation R on a set A fails to be reflexive, we can upgrade the relation to a new relation, which I'm going to denote by, if R is the original relation, R super RC. RC stands for Reflexive Closure. And the relation here, the reflexive closure, is defined this way. A is related to B if either A was related to B under the original relation or A equals B. In terms of the graph, what you do is you just add any missing loops to the graph. Then every vertex has a loop and it is now reflexive. You've done as little as possible to turn the original relation R into a reflexive relation. Another way to look at it is, in terms of the sets, is that the reflexive closure of R is R union the diagonal relation. And it's not difficult to see that the reflexive closure is the unique smallest relation on A that includes R and that is reflexive. And that's why it's called the reflexive closure. Closure refers to the idea that you've increased something, but as you've increased it as little as possible to accomplish your goal. The reflexive closure, for example, of the less than relation, say on the real numbers, is less than or equal to. The reflexive closure of proper subset relation is the ordinary subset relation, less, contained in or equal to. You can go in the opposite direction too. If you have a relation that's reflexive, you can define an irreflexive relation R prime by A is related to B under R prime if A is related to B and A is not equal to B. So you strip away the loops from the graph. We can do something similar if a relation is not symmetric, or even if it is, you can still apply this, it just won't do anything. So if we have a relation R on a set A, we can upgrade that to a symmetric relation by taking the union of R and R inverse. In other words, every time there's an arc from A to B, you toss in an arc from B to A. You add as little as possible to make the relation symmetric. Throw in those arcs and only those arcs you need so that whenever there's an arc from one vertex to another, there's an arc in the opposite direction. That would be called the symmetric closure of a relation. Finally, we have the transitive closure. relations that fail to be transitive are a pain in the neck in many ways. But if a binary relation should fail to be transitive, we can upgrade it to what we would call the transitive closure. There we need to add as few arcs as possible to make the resulting relation transitive. That's a little bit trickier than the other two cases. It's not enough to just look at paths of length 2 in the original relation and adding that third line to make a triangle. Because when you add new lines, new arcs, you may create new paths that need to have additional arcs added for completeness there. So it's a chain reaction. You make one change, it may cause you to have to make additional changes. So the way that transitive closure is described is in this definition. Let R be a binary relation on a set A, should be the word on. The transitive closure, which I denote by R super TC. I don't know that this is standard notation, but it's convenient for us anyway, is defined by specifying that A is related to B under the transitive closure if and only if there's a finite sequence of elements of the underlying set that form a relation chain. So starting at A and ending at B. So A, which I'll call A1 also, is related to A2, which is related to A3 and A4 and so on, up to AN, which is B. In terms of the graph, A is related to B if there is a directed path from A to B, and it doesn't matter how long it is, as long as it's finite, of course. So you have to complete all the paths, not just all the triangles, so to speak. If a relation is already transitive, you don't have to do anything. Here's an example. Consider the relation that consists of the vertices and the solid lines. I started to add some additional arcs to complete some of the triangles. So for example, paths of length 2, in other words. V1, V2, V3, there's a path here. This is going to have to be added if we want the transitive closure. Similarly, V2 to V3 to V4 requires we add V2 to V4. And V6, V2, V5 requires we add V5, V3. I'm sorry, V5, V2, V3 requires we add this arc. So I've added 3 arcs as a starting point. We're not done, though. As I said before, the addition of these new arcs is going to cause us to have to reevaluate. Every time a new arc is added, you have to check to see what else then needs to be added. And it may involve that new arc. So it's a little bit, can be a little bit tricky to complete a graph and get the transitive closure. And I'm going to leave it for you to figure out how many more arcs need to be added in order to arrive at a relation that is transitive. Since the transitive closure is the most common of the types of closure, a question that will arise is when we do pass to a transitive closure of a relation, might we lose some of the other properties like reflexivity and so on? You add arcs to a graph, or you add ordered pairs to a relation, who knows what might change. So here's the theorem, and I'm leaving the proof for you as good practice. Let R be a binary relation on the set A. Reflexivity is preserved in passing to the transitive closure. In other words, if R is reflexive, so is the transitive closure. Okay. Symmetry is also preserved. If R is symmetric, so is the transitive closure. Anti-symmetry is not necessarily preserved in passing to the transitive closure. You may lose anti-symmetry. So those are things for you to think about. It'll give you some good practice working with relations and these properties. Since a binary relation is just a subset of the Cartesian product, a relation on A, a subset of A cross A, we can apply the basic set theoretic operations to binary relations of this type: union, intersection, complement. So as you'd expect, the complement, which I'll denote by superscript C, of a binary relation is just given by A is related to B under R complement if and only if A is not related to B under R. So the complement of the relation of equality is the relation not equal to. And the complement of the relation less than or equal to is greater than. As to the union of two relations, R and S, A is related to B under the union if A is related to B under R or A is related to B under S. So union goes with disjunction, or intersection goes with conjunction. A is related to B under R intersect S if A is related to B under R and also under S. So here's an example, and it's hardly worth fussing over because we're just taking the union of two relations. Here's the ordered pairs for R, here's the ordered pairs for S. You take the union and you take the intersection. So that's pretty straightforward. The union of the relations less than and equal to is less than or equal to. The intersection of these two relations is empty because you can't have two real numbers A and B where one is less than the other but they're still equal. This is a little more interesting. Congruence mod K. What would be the intersection of congruence mod 3 and congruence mod 5? To answer this question, as in many cases, we have to go back to the definition. First of all, the definition of intersection says that M is congruent to N mod 3 and M is congruent to N mod 5. This is the definition of congruence. 3 divides the difference and 5 divides the difference. But since 3 and 5 are relatively prime, an integer n is divisible by both 3 and 5 if and only if it's divisible by 15. So m is related to n under the intersection if and only if 15 divides the difference, if and only if m is congruent to n under mod 15. So the intersection of of congruence mod 3 and congruence mod 5 is congruence mod 15. You multiply because these are relatively prime. If we consider this case, congruence mod 6 and congruence mod 8, then the intersection would be like this. It's the same as we did here, except now the divisors are 6 and 8. A number such as m minus n is divisible by both 6 and 8 if and only if it's divisible by their least common multiple, which in this case is 24. So the intersection of congruence mod 3 and congruence mod 5 is congruence mod, this is 6 and 8, is congruence mod 24. It's not congruence mod 48, 6 times 8. It's the least common multiple of these. Okay? And in general, I'm going to leave it for you to check that the intersection of congruence mod k and congruence mod j is congruence mod the least common multiple of k and j. That worked also for 3 and 5. Their least common multiple is their product because they're relatively prime.